We just introduced that if characteristic equations have no multiple roots, we could write the expression of an directly. However, there are different situations for roots. For example, there might be multiple roots. Let's look at this equation. For example, recurrence relation an minus 4an minus 1 plus 4an minus 2 equal to 0. How should we solve such a recurrence relation? Now let's discuss how to deal with a case when it has multiple roots. So we could say that if there are multiple roots, for instance, there's such a recurrence relation an minus 4an minus 1 plus 4an minus 2 equal to 0. The initial values are a0 equal to 1 and a1 equal to 4. And first, let's assume that we don't use characteristic equation, and we choose the original method, which is to use the generative function. We multiplied corresponding powers and the recurrence relation. For example, x squared is corresponding to a2 equal to 4a1 minus 4a0. X to the third power is corresponding to a3 equal to 4a2 minus 4a1. So we multiply x squared to both sides of the equation, and we also do the same to x to the third power and add both. And then finally, we would get an expression about the general function. We ignore the detailed process here. And the result is that ax equal to 1 over 1 minus 4x plus 4x squared. Here, we use the same method to try to convert it to a sum of multiple fractions. 1 minus 4x plus 4x squared is exactly equal to 1 minus 2x squared. And we also know that for the expansion of polynomial, we have formula that 1 plus x to alpha's power, in which alpha could be any real number, even a negative number like minus 2 here. So now it's equal to alpha times alpha minus 1 until alpha minus n plus 1. Divided by n factorial. So we could subtract the 1 minus 2x to the minus 2's power to the formula and add them together. After simplifying, it becomes sigma of k. K is from 0 to unlimited. Say k plus 1, k times 2 to the k's power, x to the k's power. With this expression, we could write ax as the x to the k's power with coefficients. We would find that the coefficient is k plus 1 plus 2 to the power of k. So for an, the coefficient of x to the nth power is n plus 1 times 2 to the nth power. So we now have the solved general term of this recurrence relation is n plus 1 times 2 to the nth power. The method we used is generative function, and could we use characteristic equation instead? For example, here we could write this characteristic equation, which is also called the character polynomial, is x squared minus 4x plus 4. It has a double root because it could be written as x minus 2 squared. So 2 is a root of multiplicity of 2. For this generative function form, the double root means that the denominator should be 1 minus 2x to the square. What about the numerators? It's a monomial with a lower order. So we use ax plus b to denote it here, in which a and b are undetermined denominators. Let's analyze that we could convert such an ax to a sum of partial fraction a over 1 minus 2x and b over 1 minus 2x squared. When this could be simplified to the original form of ax, the value of a and b are the answer we want. We want that now 1 over 1 minus x squared could be expanded by formal power series to k plus 1 times x to the k's power, in which k is from 0 to unlimited. So here, 1 over 1 minus 2x squared could also be expanded. So after expanding, we discovered that the a term is in the 1 over 1 minus ax, from which we already know how to solve. It's written as a 2 to the k power k times x to the k's power with a in the front. What about b term? Actually, it's 1 over 1 minus 2x squared. So we could write 1 plus 2x and so on times 1 plus 2x and so on here. We multiply them together. Finally, after checking it, it becomes 1 plus 2 times 2x plus 3 times 2x squared and so on. So for an, we discovered that it consists of two parts. 1 is corresponding to coefficient a. It's actually a to the kth power times a. Here, an is equal to a times 2 to the nth power. What about another term b? We discovered that its coefficients are partly from 2 to the nth power, and as it becomes a product of two expressions, the remaining coefficient is actually n plus 1. With further simplification, we discovered that 2 to the nth power corresponding to an could be taken out. What's remained? It leaves a constant plus b times m. In order to differentiate the constant with the original a, we use a prime to denote it. So an could be written as a prime plus bn times 2 to the nth power. So the undetermined coefficients are a prime and b. Here we have initial value a0 equal to 1 and a1 equal to 4. When subtracting n equal to 0 in a prime is equal to 1. When n equal to 1, we already know that value of a prime, so 1 plus b times 2 equal to 4. So the solution is that a prime is 1 and b equal to 1. an equal to n plus 1 times 2 to the nth power. Here we would find that no matter using general function or characteristic polynomials, finally we get the roots of their characteristic polynomial are still the foundation of the kth power. However, the coefficient changed. So we discovered that we get the same result by different methods, and we find some regular patterns for coefficients. Let's look at the more general case. For characteristic polynomial cx, if it has multiple roots, like x minus 2 to the square, in the previous case, assume that beta is a root of cx with multiplicity of k. Now we simplify gx further, and it could be written as a 1 minus beta x to the kth power. It could be added from first power to the kth power, and we have undetermined coefficients aj. How do we solve them? This is what we are about to do. Here we will use the binomial theorem to expand the expression. When alpha is a real number, we have that after substituting the coefficients of a to the nth power in, and using this binomial theorem, we get aj times c j plus n minus 1 n, in which j is from 1 to k. Of course, the corresponding root beta is still here. So we will discover that with characteristic polynomial, we could also use multiple roots and undetermined coefficients with a combination number to get the expression of an. Of course, this combination number is quite complex. Is there any simpler method? We have such a combinatorial identities that as j is a variable, say j plus n minus 1 n is equal to j plus n minus 1 j minus 1, and j is from 1 to k. So here the highest possible power is k minus 1. So we have that this term is actually a j minus 1's power polynomial about n, and the maximum value of j is k. So an is just a beta to the nth power multiply j minus 1's power polynomial about n. We are more familiar with polynomials, so we no longer use combinations now. We could denote it by polynomial directly. Beta to the nth power is written here as a characteristic root. And where is the coefficient? It becomes a k minus 1's power polynomial about n. The coefficients of the term are undetermined coefficients. They are a0, a1 until ak minus 1. In summary, if the characteristic polynomial has root beta of multiplicity of k, we could write the general term of the recurrence relation directly. As beta to the nth power multiplies a k minus 1 power polynomial about n. Let's return to this problem. How do we solve it with characteristic root? It's still an minus 4, an minus 1 plus an minus 2. A0 equal to 1, a1 equal to 4. Now let's write the characteristic equation x squared minus 4x plus 1 equal to x minus 2 squared. There is a double root. We know that we write the multiple roots here as a 2 to the nth power, as it's a double root. So the coefficient should be 2 minus 1's power polynomial, which is a linear polynomial. We write it as an equal to a1 plus a2 times n. Now we only need to know the value of a1 and a2. We already know the value of a0 and a1, so we substitute them into the expression. When substituting a0 in n equal to 0, when n equal to 0, we get a1 equal to 1. What about a1? a1 plus a2 times 1 times 2 equal to 4. As a1 is 1, so we calculate that a2 is 1. So only with these 5 lines we could solve the general term of the recurrence relation. It's a1 equal to 1 plus n times 2 to the nth power. So now we've introduced how to use characteristic polynomial when there are multiple roots. There is still one more situation. We know that there might be conjugated complex roots. If the characteristic polynomial is x squared minus x plus 1 equal to 0, how do we solve it? We will introduce it in the next section.